Ronitt Rubinfeld. I'm at MIT and at Tel Aviv University, and I work in theoretical computer science. I work on algorithms and complexity theory, and I'm interested in what can you find out about your data when you don't have time to look at all of it. Okay, so you get to see only a very small portion of the data. What can you determine about it? So just to make this a little more concrete, we often assume things about our data, that it has certain properties. So for example, we often assume that our statistical data is normally distributed, or it's Gaussian, or it's uniform, or it has high entropy. Maybe we assume it's log concave. So there's various terms that people like to assume about their data. And then once they assume these things, then many computational problems become much easier. But how do we test that the data actually has these properties? So that's what I'm interested in doing. And this is, of course, can be quite difficult when your data is over very large domains, which is the case in big data. So for example, Amazon has millions of product types. How would you notice if Amazon has a very different sales pattern in January as it does in February? Do you have to go check every single product type what the sales are, or can you do some sort of really intelligent sampling to see what's happening in the data? Another example is the small world property. And by this I mean the 6 degrees of separation property that was made famous in a Broadway musical and then a movie. And the idea is that between every pair of people, there's a connection of at most 6 people, a path of 6 people where every pair along the path know each other. And so if I want to be introduced to any person in this world, I can find a sequence of 6 people that can get me to be introduced to that person. Well, how do we know if this property really holds? There was this experiment by Millman many years ago that supposedly proved this, but there's no consensus on whether that experiment is actually true. So how could we actually prove this? And the world is very large, there's a lot of people, we're not going to be able to interview them all. How can we, in some sort of quick method of sampling, determine if the world actually is close to satisfying this property? So these are the types of questions that we try to answer. They're very hard when you have so much data that you just don't have time to view all of it. And that's where we're trying to make a difference. So at the Big Data Conference, I'm going to be talking about some new work that we're doing on testing properties of distributions based on the shapes that the distributions are supposed to have. So we're trying to test if the distribution really is a Gaussian, or is the distribution really log concave? Is it really uniform? Does it really have large entropy? And we're trying to use the shape of the distribution in order to assist us to do this in a faster way and a more generic way. So every time you give me a class of properties that you want the distribution to satisfy, I can test this type of property based on some nice characterization of the property. And it's usually some nice mathematical characterization that takes advantage of some of the geometric shape of the class. I've actually been working in big data long before it was a famous buzzword. I've been working in big data for 25 years, and I've always been interested in what can you understand about data without seeing it. There are many information theoretic questions, but there's also important issues for computational complexity that come out of it. It's so fundamental that it's had an impact in many areas, at least within computer science and statistics and in information theory. And to me, this is, I think, intellectually a very interesting area that's rich with new questions that really change the way we look at things and different angles that we hadn't seen before.